Hello everyone, my name is Karan Mehta and I am in third year Electronics Department of DJ Sangvi College of Engineering. Today's subject for the practical is design with linear integrated circuit. The name of experiment is V2i Converter with grounded and floating load circuits. The professor in charge for our practical is Mayur Parvelekar sir. So now let's see the theory of V2i converter. First of all, why do we need op-amp based V2i converter? So, if we use conventional source transformation theorem to convert voltage source to current source, the output load current is always dependent of load resistance. So, to eliminate this disadvantage, we use op-amp based V2i converter. So, first circuit is floating load voltage to current converter. In this, we connect load resistance as a feedback to this non-inverting op-amp, and by applying KCL equations and solving them, we get load current is equals to V in upon R. So this shows that the output load current is directly proportional to input voltage. And here R is the resistance connected at the input terminal of op-amp, and we can see that the output load current is independent of load resistance. This was floating load voltage converter. Now let's see the another type, that is called as grounded load voltage to current converter. In this circuit, the values of this all resistors is equals to R, and here we have connected the load resistance. So again, by applying KCL equations and solving them, we get that IL is equals to V in upon R, and here again we can see that the output load current is again independent of the load resistance. So this was grounded load voltage to current converter. Now let's draw the same circuits in our LTSpice window and see the simulation. So I've already created the circuit for floating load V2i converter. Now let's run our schematic. Select DC operating point and click OK. Close this window and click at this node. Now again right click at this and clear the dollar symbol and select IR6, which is the current flowing through our load resistance. Click OK. So for value of R is equals to 4 kilo ohms and input voltage as 3, we get load current as 749 microamperes. Now to verify, let's change our value of load resistance. So now I've made the value as 10k. Again run the schematic. So this means that even if we change the value of our load resistance, the current flowing through our load resistance remains the same. Now let's take a look at grounded load V2i converter. So I've also made the circuit for grounded load. This here is the circuit of grounded load, and here is our load resistance, and here is our input voltage. So let's run the schematic. Again close this window. Click on this point. Now again right click on this, clear the dollar symbol and select IRL, which is the current flowing through our load resistance. Now again to verify, let's change the value of load resistance to 10k and run again the schematic. Close this window. Now again, as you can see, the value of load current remains the same. Again let's change this value to 20k and run the schematic. Close this window. Again, as you can see here, the value of load currents remains the same even if we change the value of load resistance from 1k to 20k. But if you have realized that the value of current, output current in both of the circuit is in microamperes, this is a very less value of current. So what if we wanted a higher value of current? Instead of microamperes we needed milliamperes. So for that, we saw in theory that the output current is directly proportional to the input voltage, and the formula for output current is V in upon R, where R is the value of this resistance. So if the input voltage is limited, by reducing the value of this resistance we can get the desired current. So let's check if that is possible. So now this is our given condition. The value of output current should be 4 milliampere for input voltage equals to 1 volt. So by this we get the value of R as 250 ohms. So I've changed the value of resistance, that is 250 ohms. Now let's run our schematic and let's check the value. Click on this point again, right click on this, delete the dollar and select IRL. Now as you can see here, the value of load current is equals to 3.99 milliamperes, which is approximately equals to 4 milliampere. So we achieved our load current. But now let's verify by increasing the value of load resistance. So as you can observe here, the value of load current also changed with value of our load resistance. So this destroys our motive of making a load independent V2i converter. This is because if you observe here, the value of resistance is 250 ohms. Here at the input terminal it is also 250 ohms. So ideally the input impedance of an op-amp should be infinite, but we are reducing the value to 250 ohms, because of which op-amp does not behave properly. So if we want high values of current for our same input voltage, we cannot achieve this goal by making a homebrew circuit using op-amp. For this, we required a special function IC which are ideally made for these conditions. So now let's look at XTR111 IC, which is a specialized V2i converter IC. Let's see their functional block diagram. So this is the functional block diagram of XTR111 IC. In this, as you can see here, they have used op-amp as an buffer, because of which the input impedance of this circuit becomes infinite. And again here you can see that they have used a current mirror, which is used to increase the gain of the system, due to which the value of output current increases. Now in this circuit, at pin number 7 we connect a resistor R set, which decides the value of output current. Here we provide input voltage, for which we could get a desired output at the load. So in this circuit, even if we change the value of load resistance, that would not change the value of current flowing through the same. So in this experiment, we saw how we can make a V2i converter using an op-amp. We also saw that if we want a low voltage, low current at output, we can use op-amp. But if we want a high efficient V2i converter, we cannot make this using a homebrew circuit. For that, we need a current mirror to increase the gain of the system. And then we saw the functional block diagram of XTR111. The simulation files of this experiment are given below in the link. Thank you.